All right. So the recording is on. So I think we are good to go. So welcome everyone to the winter session of the webinar series dedicated to research topic of vector symbolic architectures and hyperdimensional computing. Cool to see you all back. I hope you all stay healthy despite of the situation. Today we have two great talks, one given by Peter Sutor and another one by Kenny. So let's go directly to the talks. So without any further delay. So Peter, your talk is first, please.
All right, thank you. Okay, so hi, my name is Peter. I'm a PhD student at University of Maryland. I'm with Giannis's and Cornelia's lab, if you guys know them. And I'm sort of new to the topic of hyperdimensional computing, and that's mostly what I'm going to talk about here. And I have this impressive title here, at least it sounds impressive, a neural network-like mechanism for learning with hyperdimensional vectors. So I'm going to talk about this idea of doing something like a neural network with hyperdimensional computing. And hopefully this is going to be a good starting point for a lot of people to start thinking about things like this and how they could be useful. So the structure of this talk is going to be as follows. I'm going to first introduce a few things, and then I'm going to talk about two papers that have been published prior. The first one is hyperdimensional active perception, which was my first attempt at using hyperdimensional computing for a practical task. And I'm going to hopefully show through that somehow what I did in that paper sort of substituted what a single layer neural network would do. The second thing I'll talk about is a paper on symbolic representation learning with hyperdimensional computing, and that is, again, demonstrating some of these properties. And then I will hopefully spark some inspiration by talking about how you can extend what I did in these two papers to something that's more complicated and looks more like a multi-layer neural network than anything else. And I'll talk about a little bit about how that works. So let's begin, I guess. I'm going to focus, of course, on hyperdimensional computing and hyperdimensional vectors, which I'll just call hypervectors from now on. And this is a MAP-B type of structure. So these are just regular binary bits distributed normally. And this is a very interesting thing to me, at least, because of the potential for these hypervectors to be a sort of like universal currency for learning. Something that you can encode any external stimuli into this and then learn from it, ideally. And I'll show you maybe why I like that idea. And of course, these vectors are also very fast, and that's a nice property. That's a nice property to have for learning, especially with how, as time goes on, neural networks tend to be, well, more and more computation intensive and hardware intensive. So first of all, I'm going to talk about the first paper, hyperdimensional active perception. And this focuses on a very specific task. This task is given an event camera, which I'll talk about in a sec, try to figure out the ego motion that an autonomous vehicle is experiencing. So can the autonomous vehicle figure out where it's sort of going in 3D space and predict that? Now, this is, of course, an essential thing for any autonomous system to be able to do. So it's a very good practical task to look at. and look through the lens of hyperdimensional computing. So I'll first talk about the DVS camera that we used. The DVS was sort of the first major event camera that became popular. And the idea of these event cameras is pretty much to see not pixels, but events. And these events are essentially sort of like individual cameras that asynchronously record what's going on. And whenever they see a change in intensity of light or whatever, it will react as an event in time. So these cameras actually see in 3 dimensions the XY position of the event and the timestamp at which the event occurred. And they're extremely fast cameras, so they go on the 5 microsecond scale of events. So events could come in at any asynchronous 5 microsecond intervals. And when you see these things, they sort of work like the Jurassic Park version of dinosaurs, where if you're not moving, nothing is happening in the camera. You see nothing. It's only when things move that you actually see something. All right. And you can see I have an example of a far better event camera by Prophecy. And you can sort of see what the RGB camera sees and what the event camera would see. And you can see in the lower picture that you only see the people moving and nothing else in the image because nothing else is moving, right? What this means is that these cameras are producing very sparse image data, basically. It's extremely sparse. And this is a good place to sort of abuse the properties of hyperdimensional computing, because when you have these sparse images, it makes a lot more sense to encode the data in hyperdimensional vectors, for example. I'll first talk real quick about a slight trick we did before I move on. One of the co-authors, Anton Mitrokin, in the past, he already was working on these event cameras and developed this sort of method of binning an interval of time, binning the events, and then projecting through it in a sort of way that he minimizes, and that causes you to sort of see the motion that's happening in these event cameras. So on the left, you see the raw data stream over time. And on the right, you see what he would produce, which is an RGB image, basically. And in the image, things that are green are events that happened just recently, and blue are older events. So you can sort of see that what's happening is it's moving sort of up, right? And that's causing these green bars at the top and blue at the bottom, all right? So we first thought about encoding this as hyperdimensional vectors. And we didn't do anything too crazy. We distributed hypervectors equidistant from each other in a certain way so that the further an RGB value or any value is from other values, the further they are in the hyperdimensional space. And that's sort of roughly incremental. So you could see this little heat map for what 25 values would look like in this sort of encoding, and the Hamming distance on the right. And with that, we basically just took an image and encoded it. This is a nice visualization of these values. On the left, you'll see the value of 0, and on the right is, on the right is the value 0 as it differs from the current value on the left. And on the left, you see the values as they differ from the previous value, where red is a flip from, I believe, 0 to 1, and then blue or white is from 1 to 0. So just real quick so that it's clear how we did this, this is how we sort of looked at values in this hyperspace. And from that, we encoded our time images as basically sequences of information. We chose a row and a column permutation pattern, and then we just use that to denote where a pixel, or an event in this case, happened, and the RGB value that it experienced at that time. And the RGB value itself is a sequence as well. So nothing too complicated. Now let's get to the actually interesting stuff here. First, what we did, just as a simple preliminary, is take just regular time images and run it through CNN, see how it performs. And you get about 7 centimeters per second accuracy in the Iga motion. So it's down to that accuracy. And we use the basic PilotNet CNN to do that with slight modifications. And then we just tried taking these hyperdimensional encoded time images and putting it through a fully connected network, a relatively small one, about 6 layers. And we get in about the same ballpark of accuracy, so 9 centimeters per second. And yet, you know, the data used has been compressed 270 times. And of course, we didn't use a CNN. So that's already an indication of something impressive going on here. Then that brought us to the next idea, which was, can we make this entire pipeline of using event data and inferring ego motion from it completely out of hypervectors? And so that's what we did. I mean, this is the so-called hyperdimensional active perception paradigm. In A here, you see a drone come in. It experiences some kind of ego motion denoted by the red arrows. It also experiences events denoted by the blue, B over here, which you can see them in time. And it converts this information into time images, which are then converted into hyperdimensional vectors based on the encoding paradigm from before. And we basically pair these up together in a special way and use that to do inference of ego motion. So given a novel image like C, we find which sort of memory created in B matches that. And the specifics of this are actually very, very simple. We encode the ego motion vector as time images and pixel values. And from this, we form memories called, a memory vector called M, I suppose, which consists of memories. These memories are basically what was the time image that it experienced for this ego motion. And you know, in order to do that, because velocities are continuous, we basically made a very discrete amount of bins and said, well, anything that falls within this bin is going this velocity. And the memories themselves were formed by just aggregating the hypervectors experienced for a particular ego motion denoted by a corresponding identification vector V. And then we just aggregated all those, and that was our memory. And if you wanted to then figure out or infer which velocity is being experienced, you simply compute, given a novel time image A encoding, you compute the XOR of that with the memory M, and XOR it with all the values of V, the velocities it could experience, until you find the one that matches the best. And then we tested this on a well-known autonomous vehicle data set, MVSEC, and basically saw what would happen with that. This is a bit of a more visual representation of it, of the memory hypervector M. If you find the matching velocity, it must be because the learned examples basically collapsed the aggregate function there so that it's the one non-random result that you get. So it's something that sticks out as being very non-random, and that must be the matching velocity. So here's an example of one of the results. This is for angular speed of the autonomous car in the MVSEC dataset. And the little heat map up here shows how likely it thinks a particular velocity is the correct one. You can see a clear path sort of in here, which is exactly the path it takes down here in the predicted values. And this is actually very good for angular speed. Angular speed is very hard to get right. A neural network won't do much better than this. It'll do slightly better. For the linear speed along the z-axis, it actually does quite good, on par with the neural network. And in the x-axis, it also does very well, as you can see. So we basically achieved pretty much not quite neural network results, but in the order, in the ballpark of it. As you can see here, these are more detailed results. We took the outdoor day 1 data set and applied it to the rest of the data sets to get these results. And these numbers are actually fairly close to what you would see with a CNN-based solution to this. But the thing is that this model is ridiculously tiny compared to a CNN solution. It's essentially only a few dozen kilobytes. And that's quite impressive, actually, that it can do this. Mostly because the training time is minimal. In a matter of a second or two, you can actually train this model completely from scratch. And the inference time is literally thousands of times faster than a CNN is to predict ego motion, which is very important because on an actual drone, you probably would have trouble having a CNN of that size do that. You would need a big drone and a big GPU processor attached to the drone. But this we did with just a regular CPU, actually just one core. And you can further train this. I mean, there's no reason you can't aggregate more results and basically train it on the fly or retrain it from scratch completely. And we found that actually after just a fraction of the data, 10% of the training set, whereas the neural network would use 70% or thereabouts, depending on how you split it. It already reached its optimal performance. It didn't really improve after that. And yeah. And if you think about it, what's happening here is this memory vector M basically replaced the role of the fully connected layer in our original test, where we just used the encoded time images and fed it to a fully connected neural network and got worse results than this, actually. So this vector, this hypervector M, seems to be replacing the role of the fully connected layer. Another study that we did looked at, well, okay, what if he did this at a symbolic level? For example, the problem of classification. The issue with full RGB images is there's no effective way, at least that I know of, to turn them into a single hypervector. So what we did is, okay, suppose that we had something that could give you a hypervector out of an image. And what we ended up using were actually hashing convolutional networks. And can we use those to sort of bootstrap this process and then replace the fully connected part that you would normally use for inference with hyperdimensional vectors? And it turns out that's the case. And this is sort of what the pipeline looks like. This memory vector M, from this point on, we dubbed the hyperdimensional inference layer because that was its role. It's essentially a hyperdimensional vector that just performs the inference. And the pipeline is very similar to the last situation where you have a bunch of training images. The hashing network computes a very small binary vector, which we project into hyperdimensional space, and then we aggregate those together, and each class has an identifier with which it binds and it aggregates in the hyperdimensional inference layer. And that's essentially the same thing as the hyperdimensional active perception. And this is just an alternate view, and I guess I already explained this. we actually ended up trying a variety of these hashing networks. Why? Because we wanted to see if you can also fuse completely different networks together on the hyperdimensional inference layer. This isn't so much important to the content of this talk, but the point here is that each network does something different. They don't learn the same way. They actually learn very differently. And there's 3 of them, DQN, DCH, and DTQ that we use. If you wanted to do a consensus between them all on what the correct output class should be, we simply made another hyperdimensional inference layer of just the 3 classes. And that's very cheap to do. So here are some examples of the results that we got. DQN here on the left shows the F1 score with and without the hyperdimensional inference layer, the yellow being with the hyperdimensional inference layer. So you can see that very quickly in very few iterations, DQN is already reaching better performance. It seems that the hypervectors bootstrap the remembering process of the hashing network pretty well. On the right is its accuracy given the Hamming distance ball that you're going to consider for the closest match. So the bigger this number is, the bigger the Hamming ball, and the more likelihood that you have a false positive in there. And as you can see, it doesn't really matter what you use for that. You'll get the peak performance that DQN would have gotten anyway. And you get similar results in the other networks individually, which is interesting. But then the more interesting thing is when you use the consensus architecture, you actually improved almost 10% relatively from the best network for free by integrating all of them. The hyperdimensional inference layer literally adds no computational requirements in addition to what you would need to run these convolutional networks. They're pretty expensive networks, to be honest. They're quite heavy considering what they do. But you have all this flexibility here. I can add or remove these networks at will. I can add more training examples. But again, you reach a sort of peak of what the hyperdimensional inference layer can do on its own, as we saw in the previous example. So there's a sort of weakness going on here. And the weakness is that the hyperdimensional inference layer only has a certain capacity to learn. And we are interested in improving that. And that is where we come to this idea of, well, what if we had many hyperdimensional inference layers? So let's make an intriguing analogy. Consider a regular multi-class perceptron. You have your input vector, the weighting process, the summation, and then the output class. These are very similar to the operations we do with the hyperdimensional inference layer. In fact, there's an intriguing analogy here to a multi-class perceptron. So what would it look like if you had a multi-layer perceptron analogy to the hyperdimensional inference layer? And this is sort of what we arrive at if we think about it from that perspective. You have many layers, L1, L2, and so on up until LM. And each layer essentially has something like a neuron, which is a particular identifier for each neuron. And at the end, at the L out, you just have the class identifiers if you're doing classification. But how would while it's clear you can make this analogy, it's not clear how this would actually work in practice, just looking at this. So part of my research from this pandemic is figuring out how this could work. And here's an example of how it could work. Suppose you had a matching path through this, we'll call it a hill net because I can't think of a better name for it. This hyperdimensional inference layer network. You have this path, shown here in red, of best matching neurons, I guess we could call them, to get to the output, which is the correct class, let's say. And the computations you do along the way are as follows. You XOR with the layer itself, then you XOR with each individual component until you find a good one, such as J1 here. And then you carry that result forward and again find the best matching one to get J2, J3, and so on. And those are the indices of the correct path through this network to get to the result. Now, how do you train this though? It's clear how this would work, I guess, how we would infer the correct class, but what's not clear is how you would get a network that can do this out of these hyperdimensional inference layers. So here's an example of how it could work, I guess. Of course, this is very rudimentary. You can improve on this massively, and part of my research has been to do that. But each of these neurons in each layer, with air quotes, neurons, they are an aggregate of training examples. That's our assumption here. And like in our previous case studies of hyperdimensional active perception, the symbolic reasoning example, you sort of match something to this aggregate, some memory, and that triggers a non-random result. So the output, the hypervector, is not random looking. So our goal is to find a path that's minimal. That is our initial assumption. And initially, we can assume that the training examples are not trained, so they're just random, which you can conceptually think about as just a single training example that is just actually a random vector. Now, the actual idea of training this is relatively straightforward if you think about it. At training time, suppose you have a completely uninitialized or untrained HillNet, you find the best matching path, which is random, of course, and you're going to compute some kind of error once you enforce the correct class at the last layer. And we'll call that Z out. Now, Z out, you'll realize that you want that to actually be 0, or in other words, you want the value that the net computes, Y, with X, when XOR with Z out, to be 0. Which you can then sort of reorganize a bit with the last layer and realize that, wait, that means that the error of the previous network is actually very much computable here. And that's what should be in the training examples for this to work. And you can repeat this process all the way back, which sounds a lot like backpropagation, right? And that's essentially what this is. As you compute this recursively backwards, you're computing what you should have done in order to get the result and what the weighting of the network should have been to get the correct result. Because of the aggregate nature of this, though, if you add more training examples like this, it doesn't actually increase the error of the final result as you're training too much. And there's a lot of technical issues with this basic approach, but it does actually work. It does improve, for example, on the previous examples I showed. You can actually continue training these hyperdimensional inference layers more so than you could with a single layer. All right, so that was sort of the goal of this talk, is to show that you can perhaps think about having these multiple layers of inference and do, and in essence, they work somewhat like a neural network here and perform backprop. But there's issues with this, some of which I list here. The bundling operation is pretty expensive, and you're doing a lot more of that here, and a lot more modifications of it than you would in the original hyperdimensional inference layer. Single paths are usually not enough. You have to introduce some form of redundancy here to actually get this to work. And one of the ways I was exploring, but I haven't yet gotten to work, is essentially consensus by trying random paths to this. Yeah, but that's pretty much it. here are the references to the papers I specify in this talk. And that's about it. Thank you. And any questions?
Thank you very much, Peter. So I guess you don't hear the applause, but they come. They go to you.
Don't worry, I'm used to it.
All right. So we have a couple of minutes for reflections, feedback, or questions. Anybody? So please unmute yourself. So.
Yeah, I have a question.
Mm-hmm.
Hello, Hedda.
Hi. You said on one of your slides
Mm-hmm.
that the training was, I think you said it was much faster than CNN.
For the single layer or multiple layers? I assume the single layer version back here somewhere.
Yeah, before you went into, yeah, this one, yeah.
Yeah. Okay. Yeah. So this thing basically. Yeah.
Yeah. So it's much in a little bit.
I think
well, approximately it requires.
Lost you, no?
Yeah.
Did you hear the question?
Yes, I heard the question. Yeah. So it's basically the computational complexity of it increases linearly with the number of layers. There's not too much more that you do. The training time is a bit more intensive because you do a lot more aggregation in it, but it's still like ridiculously fast. It's some constant times linear slower than the single layer, but that's pretty negligible for something when you're comparing it to a CNN. At least I think this is still going to be hundreds of times faster than training a CNN that gets the similar results. So that's pretty much how much slower it is. It's very much linear with the number of layers that you put in.
Oh, okay. Okay.
Yeah.
Oh, that's great. Great result.
So Peter, can I Graham Bain, can I ask just a question about that? So you've done an awful lot of work before you create that layer.
Yes.
You've chosen the features and you've done a lot of processing to create the features. So
exactly.
It's not really a fair comparison. I mean, it's more of a transfer learning would be
somewhat. Yeah, it somewhat is. But I mean, if you think about it, even a CNN didn't, like, even when you did, for example, image processing way back when, without a CNN, it didn't do very well. The fully connected layers didn't do very well. The point of the CNN was to get these better features to the fully connected parts of it to improve it. Yes, that is definitely missing here. I think that's one of the points I have at the end for future work that does not solve the issue of turning data into hypervectors and back. That is still a very big issue to get effective hypervectors here. We're essentially using the time images in the first example as a crutch, and we're essentially using the hashing networks in the second example as a crutch. The goal here was only to improve those formulations already, basically. Only the inference layer part of it. So it's sort of like a cheap improvement to performance by focusing on the hyperdimensional part of it.
We have one question in the chat. So it's about the hashing networks, so the output from the hashing networks. Is it
Sure.
Are the vectors from hashing networks binary?
Yes, they are actually because it's much
sparse?
faster. Yeah.
Are so dense?
Yeah, and they're very low dimensional. You can set how many bits to make them, but you don't want to really do more than a few dozen. So like 40 or 50 bits is more than enough. Anything more than that, and you're going to start getting very long training times. As you can see already here, it was pretty bad you needed hundreds of iterations to make improvements. That's because we're already stretching the limit of it by choosing, like, for example, 100 bits to train for. But yeah, they're just binary vectors, and we simply just project them. We repeat the pattern over and over again and project them into the hyperdimensional space. So they're not really hyperdimensional vectors at conception. There, we sort of fake that. Mostly because it's impractical to make like an 8,000-bit hash. It'll take very long to train.
So Peter, it's Graham again. So when you do that projection, are you just repeating, or are you doing some sort of random projection?
No, we're just repeating it. We're literally just repeating the pattern.
Okay.
We actually chose the length of the hashing network's output to be such that you can repeat it evenly into the 8,000-bit vector.
Right. Have you tried it with a random projection?
I have not, actually.
Okay.
I have not. Do you think that would do better? Sure.
Well, I sent you some stuff ages ago on the random projection we were doing.
Oh yes, you're right. Yeah.
I'm just
Okay.
wondering. Yeah. Okay.
That's interesting. It's interesting to think about. And actually, I was thinking about doing that for the network too, but it's hard. The math is hard to sort of figure out how that would work. So I opted for something much simpler here to make a point, I guess.
Yeah.
But yeah, it's an interesting idea.
Thank you.
Hi, this is Pam.
For comparison, you can also probably run cellular automata. So Dennis has published a paper on the archive recently,
Right.
where he shows how dimensionality can be expanded using cellular automata. So if you have a small vector, so you put it as an input, you initialize cellular automata with this vector, and then you run for several steps.
Is it similar at all to this in execution? How similar is it to this neural network out of curiosity thing?
So we have Dennis here. I don't know. Do you have anything?
Yes, hi everyone. Yeah, I'm not sure. I can't answer it from the top of my head. I guess I need
Yeah, I'm not sure either.
more the architecture previously.
All right. If you have any other questions to Peter, so please send them to him. So, or better send them via our email list so that we all can contribute to the discussion. Let's thank Peter once again. So great talk, interesting topic. So definitely we'll read the articles you cited.
Thank you.
Yes. And let's move on to the